This is the problem I've been looking at with Paul and Ricardo. This photo is supplied by Magda Carr. I think, am I right in thinking this photo would have been taken in St. Andrews, but then the little ones are in Newcastle, right, where you're working now? Yeah. This is the photo then from the St. Andrews lab. And the colors, the bright color approximately means rapid change in density. So where it's dark red, the density is almost constant, and you have these two pycnoclines with rapid changes in density. And you can see that we have then almost three homogeneous layers separated by some thin pycnoclines. So the goal is to try and model these waves. The three-layer case is sort of for two reasons. One is that you do find this kind of stratification with rapid changes located in the ocean. For example, in outflows in certain locations where you have saltier or colder water on top or colder water on the depending on the location. And second fold is that it's a model for higher mode waves. So if you have a two-layer flow, you have one mode of propagation, and a three-layer internal wave model. The simplest model to have a higher mode, mode 2. So the model we'll consider is going to be as following. We're going to have three infinitesimal layers of constant density. The middle layer will have density 1. We'll denote properties of each fluid 3, 2, and 1 for the bottom, middle, and top layer respectively. We choose y equals 0 at the bottom, where the origin is. The depths of each fluid is not quite the undisturbed depth for numerical reasons. We choose to take the depth at the periodicity points. This is a periodic solution. When we fix those to be H3, H2, and H1, which sum to unity, so we non-dimensionalize with the height of the channel or the depth of the fluid. We take potential flow in each layer, and we kill time dependence by asking the question, what traveling waves exist in this system? We take a periodic domain for a very special reason. It's not just a numerical trick. It's more that we want to allow for oscillatory tails in the solution. So I can't assume the solution will go to 0 in the far field. This is because mode 2 waves oftentimes exist in the linear spectrum of the system, and you have resonance with mode 1 waves of finite wavelength resulting in what's called a generalized solitary wave. The linear theory tells you precisely that you have two modes of propagation. You get a quadratic for the c squared. You find that mode 1 we denote as c plus, and mode 2 we denote as c minus. The linear theory tells you that for mode 1, well, for starters, it's faster than mode 2. We denote by c0 plus and c0 minus the long wave speeds. So you can see a sort of a schematic of the dispersion relation in the bottom right. C is a function of k, wave number is a function, speed is a function of wave number. And it also tells you that mode 1 waves travel with their pycnoclines in phase. That is, they both go up and down together, while you get these more bulbous shapes for a mode 2 wave. These solutions are, of course, far too large to be linear, but it's more so you can see the picture. We also consider, as well as the full Euler equations, a model equation called the Miyata-Choika-Massa equations. It's best understood as a multi-layer analog to Green-Magdi equations. It assumes the flow is weakly dispersive to some order in the shallow water parameter, and that shallow water parameter should be the same for every layer. It suffers short wavelength instability. In fact, it's ill-posed, but it's often used to comment on the wave properties of steady traveling waves, where it's seen great success in a two-layer model. A paper by Ricardo, Wu Yong, and Paul, who are all in the room, showed in 2020 that traveling solitary wave solutions to this system are governed by a Hamiltonian with 2 degrees of freedom. So you see here we have rather messy expressions for the potential and the Lagrangian. You can take that as the total energy when you sum them. All of the Lagrange equations are satisfied and so on. And especially useful is this idea that its potential pops out. This V is a function of zeta1 and zeta2, a function of the two surface displacements. Here, delta 1 and delta 2 are density jumps across the first and second and third layer. And the small h's are functions of zeta. They are the total depths of the layer at the point x. Also for full Euler computations, as Phil says, we do the classic Jean-Marc 1980s computations, boundary integral methods using the velocity potential and stream function as independent variables. So you map to the potential space, you map that to an annulus, you do reflection principles, you take the Cauchy integral formula to map things onto the boundary, and then you get non-local equations of one less dimension, and on a fixed domain, making meshing the problem easy. So I think most people here know this kind of stuff. If you want to ask questions, you can catch me after the talk. We also saw this slide in Ricardo's talk. It's this idea of conjugate states. So we found looking at conjugate states and critical points of this potential can be very informative into what types of solutions one can find. So here, when you ask what a conjugate state is, the way I kind of try and describe it in the simplest way is given H3, H2, and H1 on the left, we've given density stratifications delta 1 and delta 2, what values of C, zeta 1, and zeta 2 on the right-hand side satisfy the hydrodynamic equations. It tells you nothing about whether you can get from state A to state B. So that's why I put the connection in a dashed line. That connection would form a wavefront if it exists. You might call it an internal bore, might call it a wavefront, might call it sometimes a conjugate state, but conjugate state actually doesn't mean there's a connection. It's just talking about what values of C, zeta 1, and zeta 2 will give you the, will satisfy conservation of mass, momentum, and energy. A very convenient outcome of the MCC system is that the solutions to the conjugate state equations are equivalent. Again, that doesn't mean that if there's a wavefront, they're the same profile, but the state on the right and the state on the left are the same in their conjugate state equations. MCC being a strongly nonlinear long wave model, you might expect that to turn out to be the case. This is sort of infinite wavelength type problem, right? There's no waves on the interface, so you can imagine dispersion not mattering in that equation. Furthermore, the very exciting outcome as well is that so Ricardo has shown that critical points of the potential when V is 0 are exactly conjugate states. So you choose the potential in a way for this. So again, this Hamiltonian formulation is for traveling solitary waves. So you've assumed the far field is flat, and you've chosen to fix the potential V equals 0 at the far field, okay? So you have the origin, zeta 1 is 0, zeta 2 is 0, as V equals 0, and then curves of V equals 0 in the potential space kind of bound where your dynamical system can go, essentially. So critical points of V when V is 0 that are non-trivial critical points are conjugate states of the origin. To give you an idea of how this looks, we're going to plot some potentials as a function of zeta 1 and zeta 2, track the critical points, and look at the line V equals 0 given by red. So here I have some parameter values that are fixed. It's for a small middle layer relative to the other two. And we have delta 1 equals delta 2 equivalent to a small value. And we have the bottom right quadrant of zeta 1, zeta 2. Zeta 1 positive, zeta 2 negative. So the origin is given by the top left of this image. Do I have a laser? Is it the red button?
I think it is. Yeah, you're pointing, but
there you go. Yeah. So that's the origin. You can see that you can't quite see it because the V equals 0 line goes outside the quadrant and back in, but it hits the origin V equals 0. You can see these 4 critical points in this quadrant. You have a minimum red, maximum black, and 2 saddles given by blue. And so you can see that for this value of C, that value of C, given by this value of zeta 1 and zeta 2, which you read off the axes, is a conjugate state of the origin. Now, as I change the value of C, this surface evolves and the critical points move. So if I increase C a bit further, you now see the V equals 0 line going through this saddle point. So now this value of C, zeta 1 and zeta 2 are solutions to the conjugate state equations. Any solitary wave coming from the origin that wants to come to a homocritic orbit is bounded by this V equals 0 curve. So it has to go somewhere around here and it comes back. Notice that in this case, this saddle is below V equals 0. So you might find some interesting structures. For example, you might find in the vicinity of this saddle point, the periodic orbit bounded by V equals 0. So you might well see some kind of solution that goes from the origin and tries to connect to that periodic orbit. I think we spoke with Tom Bridges, and the wording for what you call that solution.
Heteroclinic chain.
Oh, is that the name we're going for now? Okay, heteroclinic chain. Okay. There was talk of a generalized conjugate state, and there was some other. We couldn't like try to decide how to name it. Anyway, finally, when you increase C further, this maximum drops. Typically, when you increase C, the surface drops, and you find that this eventually encloses the maximum. So this is just below the value of C required for it to be a conjugate state. So you see in the bottom right quadrant, we have 3 conjugate states of the system. So I'll talk very briefly about mode 1 waves. We saw a talk by Ricardo about this, but mode 1 waves could usually be described in what I might call a typical solitary wave branch. When you want to look for solitary waves, often what you'll do is you'll do some weak linear theory to try and describe a bifurcation structure close to a k equals 0, the long wave speed. Then you would look at increasing amplitude up to some limiting configuration. So this typical solitary wave branch goes from small amplitude and broadens to a solitary wave branch. This is a solution for MCC, though you can find similar ones for Euler. In this talk, I will try and discuss the bifurcation structure by going backwards. So I'll look at what conjugate states there are, see if I can figure out any connections to them, and then work backwards. So lots of work on sort of mobile solitary wave branches has been done. Amick and Turner proved this broadening behavior. Turner and Vandenberg computed them. Grudis and Grudis some 3-layer mode 1 waves in 2002, I believe, not 2001. And Kamasa et al. Looked at the validity of MCC for a 2-layer model for mode 1 waves. So you saw this plot yesterday. This is a plot of all the conjugate states of the system given a value of this main plot is the main thing to look at. This is a blow up of this small region over here, where there's 2 red lines that kind of disappear. And then ignore this plot entirely. I need to get rid of this one. I never found it very helpful. So what I'm going to do is fix H1 and H3, delta 1 and delta 2. What this does plot is it plots all the conjugate states, but you can never tell because there's too many lines. Delta 1 and delta 2 are fixed. H1 is a fraction of H3 or a ratio there. And then H2, we vary from a infinitesimally thin middle layer to a middle layer that takes the whole channel. You can plot the speed, C0 minus and C0 plus along wave speeds. And then the solid and dashed lines are conjugate states. If it's blue, it's mode 1. And if it's red, it's mode 2. If it's a solid line, it's a maximum of the potential of the MCC system. And if it's a dashed line, it's a saddle of the potential of the MCC system. So for example, if I put H2 as 0.8, you will find you have 1 mode 2 conjugate state, which is a saddle, and then 2 mode 1 conjugate states, they're quite close together, which are both maximums. Meanwhile, if you fix H2 to be 0.1, you find just 1 mode 2 conjugate state and just 1 mode 1 conjugate state. If you decrease C further, suddenly 3 mode 2 conjugate states appear. Okay. This is the linear spectrum of the system. So anywhere where C is below C0 plus, you get linear waves that propagate on these interfaces. You can also read off the behavior of the potential at the origin. So it's a minimum, and then as you go from C0 minus, increase C past C0 minus, it becomes a saddle and eventually a maximum as you exit the linear spectrum. The criticality condition for mode 2 is here, which means that KDV theory predicts that your waves are concave over here, that's thick to thin, and convex over here, which is thin to thick. So if we start here, I'm going to look at H2 as 0.8, these values here, and look at these mode 1 conjugate states. And if I throw this in the MCC solver as initial guess, my 10H profiles, it very quickly converges to a solution that looks pretty much like it, but with a smooth connection, right? So you can compute these solutions where you increase further the amplitude, not the amplitude, the energy of this wave, the mass perturbation, and it seems to increase indefinitely. This limits to a heteroclinic orbit from the origin to a maximum of the potential. If I look at this, so one thing that's curious that happens is that this mode 2 conjugate state actually leaves the linear spectrum. So the speed of this solution here, conjugate state solution, is faster than C0 plus. So as an initial guess, you can take a solution like this, the conjugate state with 10H profiles. You can see here the solution is concave. It goes from a thin far field, a fatter middle layer in the far field to a thinner one here. And if you stuff this in your solver, it converges to a solution. But there's oscillations on this broadened section. This is precisely what I said earlier about the potential. This saddle has dropped below V equals 0. So you find in the vicinity of that area a mode 1 oscillation that you then basically almost connect to. So this solution is a homoclinic orbit that almost hits a periodic orbit existing somewhere else in phase space and coming back. You can appear to add as many of these oscillations as you want to in the numerical solution. I won't talk too much about this. 2 points is that if you find this behavior for MCC and Euler, the bifurcation structure is very rich. I won't delve too much into what the solution space is doing here because I want to talk about other things. The comparison is also good, except that I'm not trying to lie to you. I'll tell you honestly, we also say in the paper that the X scale is a bit different here. This is the mass of the bottom interface. And you can see that it goes a bit further. So there's qualitative similarities, but quantitative differences in these solutions. So the bifurcation is very rich. All of these solutions over here have speeds faster than the red one. This red solution is actually the flat conjugate state connection. So this is a wavefront solution. It's just getting broader. It's a tabletop soliton that's getting broader, and you get all these bifurcation points, and you find solutions like this there. So this is MCC in red and Euler in black, and you can see that quantitatively there's disagreement, but the overall structure of the solution is similar. You're adding more and more mode one oscillations to a broadened conjugate state, so a broadened wavefront solution, essentially. So everything I've talked about so far has been outside the linear spectrum. This is where you typically expect to find true solitary waves, localized solutions with no tails. But when you're inside the linear spectrum, things are a bit different. So taking, for example, the dispersion relation for a free surface gravity wave. You have a speed that goes from C0 plus and it monotonically decreases to 0. And you find solitary waves bifurcate KdV like from k equals 0, and they have speeds faster than C0 plus. So they exist outside the linear spectrum. If, however, I take the gravity capillary problem with bond number less than 1/3, my dispersion relationship has a minimum and then increases. And what you find is it less or greater than 1/3, room of experts. Less, I was correct.
Yeah,
Fantastic.
yeah.
Yeah. Okay. If you look for solitary waves in this region, and people have, what you find is that almost all of them, or we think all of them, have oscillations. So there's been some in the tails. So there have been some exponential asymptotic papers looking at this, which have some numerical aspects to them, as well as numerical explorations that have looked at this, and they found that it's very hard, or it seems impossible to remove these tails. The mode 1 waves we just saw, and the mode 2 waves outside the linear spectrum were somewhere over here, right? We're outside C0 plus. So they're going to a flat far field. The origins are maximum here. It's easier to connect to without hitting an oscillation around it, because there aren't any. The question is, what happens here? So now we're going to start looking at conjugate states in this region and trying to figure out if we can find connections to flat far fields for solutions, for solitary waves. So it is the case that actually people have found embedded solitary waves in the past of mode 2. It is not called it that. If you take the Boussinesq approximation by removing density into contributions to the inertial term, and you satisfy some symmetries, the top and bottom layers of equal thickness and symmetric density stratifications, you can find mode 2 solutions with a line of symmetry about the mid-depth. This is essentially a mode 1 solitary wave to a 2-layer problem using the Schwarz reflection principle, reflecting it across the wall, where you have the stream function constant, imaginary function. You can reflect it across the wall and get this upper part here. This is always going to be a flat solitary wave, this reflection. So we call such solutions, we call this configuration a symmetric Boussinesq configuration, and they are equivalent to mode 1 2-layer solitary waves. They're not the only solitary waves with such conditions, okay? You can find solitary waves that have H1 equals H3, delta 1 equals delta 2, but don't have this midline symmetry. But they're a good starting point to look for other ones. The thing is that if you break the symmetry in any way, you switch off the Boussinesq approximation, you change delta 1 to not be delta 2, or H1 to be different than H3, you find generalized solitary waves. So now all of a sudden your solutions have tails. The oscillations can occur at very small amplitudes. So following a method of Champneys et al. In 2001, they propose a criterion for identifying localized solutions. They say compute a branch of generalized solitary waves, look at the second derivative at the last mesh point, if the domain is periodic, so the first derivative there is 0. If I can find places where the second derivative is also 0, i.e. 0 curvature, I've transitioned from a peak to a trough, a point of the lowest linear wave. Trough or trough? I always say it wrong. Trough, fantastic. I'm in a room with wave experts. Okay, trough. You all know your stuff. I'm testing you. Yeah, so you've gone from a peak to a trough. And in between, you had to go somewhere where it was flat. So this is based off their argument for identifying so-called embedded solitary waves. So this is an example with the Boussinesq assumption. We have H1 equals H3 at this point, this line here. This is the symmetric solutions. You see they have, for every value of H1, the same value of H3. You could plot a speed amplitude bifurcation diagram for fixed H's and fixed rhos, like you typically would for solitary wave branches. If you break this symmetry in any way, in both Euler and MCC, you find now these curves actually have varying H3. So, and therefore H1, because you fix H2 in this case to be 0.25. So that is, there's a special solution. All these solutions are localized. In the far field, they're flat. But you find like all around them solutions with waves. This is a subset of all the generalized solitary waves. And these are localized solutions with non-symmetric heights across the interfaces in the far field. The red curves are for these values, blue for these. They're actually a reflection of each other due to the Boussinesq assumption. So you can just turn one of the solutions upside down and you have the other one if you swap the rows around as well. That's all I want to say about that. So this branch, the solutions look like this. You're now not going from the origin as a maximum of the potential. It's actually a saddle. And you see that as the amplitude increases, you're getting closer and closer to a heteroclinic orbit from this saddle to the maximum conjugate state there. So as this gets broader and broader, you're getting closer and closer. But all these solutions come back because these are all homoclinic orbits. They're all solitary waves, but the limit is a wavefront. Just to remind you that all of these things are embedded. If I change a parameter lazily, if I'm not careful how I change a parameter, all of a sudden I get an oscillation. Note that the dynamics here are not bounded by v equals 0, because the v equals 0 is the definition for a flat far field. You could be a bit more careful with how you do it to always bound it by v equals 0, but I don't really care about these solutions too much. And I like to be able to see the actual contours of the v equals 0 dynamical space. Okay, so these are sort of what we call single hump solutions. You can see that the structure is fairly simple. There are these varicose bulges in the displacements. But in the MCC system, Ricardo had this idea to look for very strange solutions called compactons. They connect a zero outer solution with these very special relations of periodic orbits inside. There's an inner solution. They match them and they find that this solution here has 1, 2, 3, 4 maximums on the top and 5 on the bottom, and it connects to a 0 solution either side. And then they found that you can open these up. So you can actually find more. This is a bubble, essentially. This is a bubble of row 2 inside row 1 and row 3. Very strange solution. But you can open these things up and find them for finite values of H2 as well. And we found that in the Euler equations, you can also find such solutions. I use this terminology N1 and 1N. That relates to how many oscillations on the top and bottom. But that's not really the best way to define it, because this definition is only holding for when H2 is actually 0. The structure of these solutions is quite delicate. I can talk about them more in the break, or I guess it's not the break, it's the end. We're almost there, crikey. After Tal's talk, just close us out. Yeah, so you can have fun with this. You can seem to stick as many of these oscillations as you want on this broadened section. And these things, I wanted to have a phase plot, I don't have it. These things are precisely, again, going towards a saddle point with the less than 0 and oscillating about a periodic orbit in the vicinity of that solution, of that critical point. You can ask how these solutions end. So like, okay, I have one of these, I can increase the amplitude, I can plot them in some parameter space. So the dimension of the parameter space is less by 1 than that of generalized solitary waves, because I'm choosing special values of parameters to find them. They're not existing everywhere, or for all parameters like GSWs are. And you can find these funny solutions as the amplitude gets larger, like here, the area inside seems to get larger and it's broadening. And actually, if you look at the phase space, it's quite intuitive. What's happening is you're approaching a periodic orbit near this saddle and then coming back. And as you increase the amplitude, it's actually getting closer to connecting to the critical point, which is almost v equals 0, slightly larger, and then doing almost a homoclinic orbit. So it seems to almost be these solutions are getting longer and longer. It's becoming more like solitary waves riding a solitary wave. You also find such behavior in Euler. So this is a comparison of MCC and Euler for quite sympathetic parameter values. We found it difficult to push it for small h2 or for additional humps. I will say that a recent formulation that was initially done in similar ways by Roussos and Gru has been looked at again by Jin, and he's got fantastic computations in an upcoming paper we're writing with him. He's done all the work for it. Really, really good stuff. Actually, it allows for H2 to be infinitesimally thin, pretty much, it seems. So we can actually see what the limiting configurations are as H2 goes to 0 for Euler now, I think. There are actually some, I've rewritten his code and I'm playing around with it, and there are some strange, because when H2 goes to 0, this middle section is becoming almost static. And we've seen with these overhanging profiles that if something's static, you can have weird things happen. You're allowed to have 120-degree angles, because the other side's not 120, but it's static. It's kind of allowed. There's a limiting configuration that's quite strange. I think this guy, as you push it to H2 as 0, is forming an angle on 120 degrees here with a static bubble inside and the fluid above, I think. In MCC, you could get like 4 or 5, and this is just where it gets silly. You can basically ask yourself, okay, what homoclinic orbits originate at this critical point? And then if I go just below that speed, I'll have almost homoclinic orbits, and you can start connecting them all together, essentially. So these solutions bifurcate from H2 as 0, you increase them, you move around parameter space, and you can find these very strange solutions that seem to combine different homoclinic orbits. So because of this two-dimensional potential, You have much more interesting dynamics than one-dimensional potential, right? There's more directions you can move.
Well, this is precisely a heteroclinic chain.
Okay, this is actually okay. Why is this here? I'm not sure. Okay, very good. Okay, so conclusions. So this is numerical evidence of Mode-2 solitary waves existing in the linear spectrum for non-trivial stratifications and non-trivial height variations. We also found Mode-2 solutions outside. That should be C0 plus. That's gone a bit weird. It should be underscore and then a power. I just put C plus 0 plus. That's not good, is it? So there should be yes, there are Mode-2 solutions that exceed the Mode-1 long wave speed. This results in multiplicity of solutions and many interesting questions about how you could generate these things. I think the main takeaway is that the conjugate states of the MCC and Euler system being the same, combined with the knowledge of these critical points of the MCC potential, make the MCC a very useful tool in trying to make better sense of the Euler classification space. I mean, these critical points are critical points of the MCC potential. They only agree with Euler when it's a conjugate state. At all of the times, it's a different system. But nonetheless, it seems that the solutions you find are all very similar. We want to, with Wuyong, regularize these MCC equations and then integrate them in time. I think a very pertinent question is about stability of these things. So if I have an initial condition in the Euler integrator, one of these solutions, will it just die? Will it radiate Mode-1 waves? Or can it actually be a coherent structure? Can it be an attractor of dynamics in the system? We also want to make this continuously stratified in the DGL equation. And also, I think the hardest question, which probably should be at the end, is can we generate these waves in the laboratory? How small would Mode-1 radiation be in that case? You're never going to get it to be perfect, but can you get them to turn up? So I include some of the existing future work. This is a picture from the paper with Jinwan, and you can see these fantastic limiting configurations for 3-layer waves, and there are many more pictures that get weirder and weirder. And this is a computation of mine of the DJL equation. I've taken a classical solution of Tung in 1982, where he computed a solitary wave that's symmetric Bussonesque with a stratification by the dash line. And I then added a non-symmetric perturbation. This is density somehow, and this is the height. And I found a localized solution with these two different vorticities in these two sections here. So it looks to me like you can find localized solutions in the DGL equation as well. But yes, I'll leave it on this slide, and thank you very much.